full course. Let's say we finish a bit the geocomputation and we are entering the machine learning environment. With this at this stage, we don't have to completely forget whatever we learned for the geocomputation, but we need to integrate the geocomputation aspect inside to the machine learning thinking. Okay, so it's really a way of thinking in a multidimensional way, and Antonio is going to explain with a simple study case how to do this transition from a linear model, let's say, in a multivariate or multi-complex relationship in a machine learning environment. He's going to build up upon difficulties. So try to stay as much as possible behind his lecture. Not behind, within his lecture. If not, is getting quite hard to follow along all the aspect. So before to give the full words to Antonio, I want to review some aspect with you. In particular, if we go to let me sharing. If we go inside to the actual the usual syllabus. Okay, you can see, click correctly. Yes, we are around here. So we are going to have today a little review of the data set in order to the estimation of the tree height that we already use it. I will just review it for 10 minutes, but then you, as strongly suggested, if you go deep inside the explanation of the data set per se, watching the video recording from last year. I don't want to spend like 45 minutes in this explanation, also because it's quite easy to follow the video recording and giving more time to Antonio for the full lecture in the introduction to machine learning. Then we will switch to we'll give the words to Antonio for a machine learning introduction, and he's going to follow up with a study case with the support vector machine using the same data set. So from now on, we're going to use only this data set. In this way, everybody gets familiar and see the potential. And then you have follow along this one with a random augmentation. This is also quite straightforward with a video recording from last year. Of course, it's from last year, so there are going to be slight difference, in some little pip install different or some. So try to troubleshooting in this aspect. So here you can click and you can open directly the PDF of Antonio, and the same for the support vector machine is going to bring you directly to the Jupyter Notebook. As usual, do the Git pull and the rsync to synchronize the data set. So let's go in the estimation of tree height. So we have been using this data set with in different occasions with 4-point extraction. I'm going to give a general overview of the data set again to give you a more understandable of what is this data set. So the JEDI data set is a laser scanning data set that is retrieving, is sending impulse to the Earth and is giving information about the tree height. Okay, of course, this tree height is not 100% accurate. Also include because it's coming back from an algorithm, several algorithms of transformation of the wavelength back to the meter of the tree height, and of course there are errors as usual. So there is always a trade back how to treat this error, and Antonio sometimes is going to use this error to improve the machine learning algorithms. The path of the sensor of the tree heights of the JEDI sensor is not full coverage of the Earth, but is in stripe, and each single stripe is in each single impulse there are different points where are retrieving the information of the backscattering process of the wavelength. There is the sensor, and the sensor is launching 8 different, actually even more, different angle and precision, different laser path, and in according to the position and to the angle, we can have coverage laser and full power laser. In other words, the full power laser is perfectly vertically, as you can see. Rather, this one, the coverage laser, is a bit in diagonal. And of course, due to the diagonal position of the laser scanning, each one has his own error, okay? When they launch this input, you can get, first of all, there's not only one point that is retrieved, but actually inside to this one is representing a bunch of points, okay? So some of these laser scanning points can penetrate through the canopy cover, and some of them, they will be scattering back from the canopy tree height, okay? And some other, they will even scattering back from branches and stem and so on. So indeed, you can have a really range of scattering process over here, where you have a big amount of impulse scattering back from the canopy cover, and much less from the tree stem, and then is increasing again when you're arriving to the understory. So the laser scanning, the JEDI has been really used in the past 3-4 years, even at the global level, for the quantification of the tree height. So there are there is one main publication that is listed over here, so you feel free to read, that is going to, this one, yes, it's that one, that is going to use it for the full implementation at global level. Anyway, there are several improvements that can be used in the algorithm development, and we will see how we can, let's say, beat the publication with a better implementation in the machine learning environment. So a part of the function are the technical details of this one, that then you can go directly from the video recording, deeply in the video recording. We will have this data set that is going to use it. And in particular, we can see that the X and Y coordinate over here, that giving information about where are these points, okay? Where are these points in the lat-long domain? Pay attention that this one, the select, means that these data have been selected by me. So there have been a lot of data cleaning, especially because some of the data set also fell. I mean, the data set, the BIM, they fell everywhere in the forest, but also in agriculture and urban. So I've been already, due to that, we are going to focus on the tree height. We don't need to having scattering process in urban area or in agricultural area. So I've been clean out all the points that they were falling inside no forest area. And the no forest area, I mean agricultural area, water, and the urban area. So we will concentrate only in the forestry points that are failing on forest, yes. Okay. And this one is due to that this was selected over here. And how I did it, of course, with, for example, with the GIDA location info, I can retrieve information if it's forest and non-forest, and then I can remove whatever is non-forest. So I maintain only the one that are captured in the forest. Then I have also the predictors. So at each point location, still with digital info or with all the other methods of point extraction, I can see at that position, which is the predictors, which are the environmental conditions that can be returned. And in particular, pay attention that over here, I mentioned also the other day, over here, estimate of tree height using JEDI, predictor extraction at point location. There are all the methods that me, Francesco, and also Olivia was proposing. Okay, so there are 4 methods of point extraction that can be useful to integrate in your scripting procedure. Like always, a model implementation, we will have always an observation versus predictors, or they also call it covariates, the predictors, or Antonio is going to use quite often the word feature. Okay, so all are perfect the same. Rather, the observation most of the time, actually, also for observation, I think Antonio is using labeling. Okay, so unless it's unsupervised classification, and we will see the difference between supervised and unsupervised, we will have always observation. Okay, in our case, we are going to use it. We are going to work with a continuous variable. So is that is the tree height. So we are going to work for regression analysis. But the same concept can be also applied in case of classification. Okay, right, like urban classification or land cover classification. So the concept is going to be pretty the same. So in particular, it's going to use this data set, and also the X and Y coordinate, this one that I just presented. There is an additional data set that is this one, that is nothing else, that not the tree height has been recorded, is being okay, you have the impulse, and then you have 6 algorithms that retrieve the tree height, okay? And these 6 algorithms, of course, they have inaccuracy and error inside to their estimation, okay? So we don't have one algorithm that is giving us the tree height 100% correct, okay? So also there, we have an uncertainty that is going to be taken into account. And the video recording is going to explain very deeply how to use also this one for the estimation. That is all this one that is written over here, so you can watch in the video recording. So just to give you an overview, these are the different data sets that we are going to use it. Some of them are the CHELSA database, this one for the climate, that are retrieving that climate. Then we have satellite information coming from Landsat, this one. Then we have a bunch of geomorphometry layers, but because you can imagine that area where there is a deep soil that accumulate a lot of water, so concavity in this context is going to produce more material, more organic and water content to have high trees, rather than a tree that is completely in a steep slope and so on. So this kind of covariate that indirectly can help in the estimation of the tree height. Some other are also related to the soil. And that's it. Yes, so we have again satellite, geomorphometry features, soil, and also soil temperature, so soil climate, soil, also type of soil. Okay, so this one of type of soil. You can see over here, you can scrolling down, and as you know, that one of the first analysis to do it is the so-called data exploration. So you always need to understanding the distribution of the data set in order, or each single data set, in order to retrieve the distribution and also potential outlier, like the one that we were seeing in some graphs that no data was popping up over here because it was not labeled correctly and so on. So always try to do this kind of analysis in this context, okay? And also because the distribution, Antonio is going to retrieve on this one to understanding how to transform the data in order to use it inside to the machine learning environment. Here also each single data set is explained. They say they show the source where they come from. So it's very well explained, and you can retrieve all this information. Okay, so keep this in mind. I think it's quite clear, the data set, and you can get more information on the video recording, but for now the only thing that you need to know is the tree height versus a bunch of environmental predictors that I just show over here. Okay. Here, nothing at the plotting procedure with Rasterio that you can go and PyPlot to this kind of plotting. And you, of course, you have also you have the tree height over here. You can see the tree height. The tree height data. This one is also inside as a Jupyter notebook inside exercise, so you can run the Jupyter notebook that is there. Okay. Pay attention that you need also to run the Jupyter notebook. If you want, you need to install some library that is the AtArtist one. So feel free to install it in advance. Okay. Is there any question concerning yes, the data set and you know, you can have these linked with any kind of modeling technique that you are trying to do it. So for example, species distribution or species distribution is the same, presence absence of a species versus predictors. Or for example, Samuel is going to do it pH of water, so observation of the pH versus predictors that influence the water. So any kind of modeling that you have always quite often presence observation versus predictors. So this is where we are going to retrieve this information and passing to Antonio for the implementation of machine learning. Okay. Any question in this aspect? Yeah.
Right.
Yes.
May I ask a little bit about this is extracting the predictors from the given coordinates, right? Given the coordinates. But I think you also mentioned about like if I want to extract the area of a stream.
Yes, in our case, this one is a point location. Okay, so there is a fundamental difference between who is doing hydrological modeling and who is doing species distribution, or in this case, tree height, or any kind of spatial modeling that is in a spatial context of that application. Because just to let you understanding for everybody, the hydrological context is not really interesting what is happening at that point, but is what is happening from that point to upstream. Because if it's raining in the upstream area, then it's going to be driven, is going to be influenced downstream. Rather, in species distribution modeling or tree height estimation, you get the information where the point is located. Okay, so it's slightly different, the approach that you have to build to use it to build up the table, but the concept is always the same: observation versus predictors. Okay. So yeah, and yeah, thanks for point, Samuel. Any other question this aspect? Today we are 20 people. Yeah. So
sorry, just a quick summary. So we have these laser scanning results, and those are observations, right? So we already have our prediction estimates of tree heights, right? So are we trying to improve those with the covariates or with the features, or estimate them?
Perfect. We're going to estimate them, especially because back to the sharing, because we, the observation are not is not everywhere.
I see. Okay, I get.
We don't need.
I came 5 minutes late. That's the piece of information I was missing.
Okay.
Cool.
Perfect.
Thank you.
So, and any times in the spatial domain, one of the main point is to make prediction outside of our observation in general, because in the observation point we know what is going on already.
Yeah.
But of course we can use it, the link we can identify the relationship between observation and our predictors in different way. Okay, there is all the band of the classical statistic it does in one direction, rather the machine learning is doing in another direction, but with common fundamental aspect between them. Okay, and Antonio is going to use this approach to explain the machine learning. But again, one of the main point is to make extrapolation everywhere based on this observation. Okay. So this is the concept that we are trying to do it, always in the context of Y versus predictors that X1, X2, X3. Milutin, go ahead.
Giuseppe, what are the training data? Is it JEDI data itself or airborne LiDAR or something?
No, this is the JEDI data that has been extrapolated by the JEDI HDF. So it's already, and this one is from the HDF, there is this scripting procedure that has been provided by the JEDI tools platform and manipulate with Python, but I tweak quite a bit to the Python script in order to retrieve from HDF and transform it to TXT that is more understandable and visible. Okay.
Yes. Yeah.
These are quite massive data set. The HDF in JEDI is like, each file is like 10 gigas, so they are very big. And this is nothing else that are very small, is only one file, but there's very small area in Germany. Okay, so so making a global implementation is something really challenging. I've been done a scripting procedure, but then they are a bit in a sleeping project.
Yeah.
But the potential are very, very
but
high.
those are basically original JEDI observations. Yeah, the height, the product, the heights. Yeah.
Yes.
But which one? Because there are 7 processing algorithms. So which one is then taken as the best one?
Yes. So just to point, this is something a bit deep in the explanation in the video recording. So there are 6 algorithms that each one provide an estimate of the tree height. But there are some cases that are really matching very, very well, like this one. Okay. So rather, there are some other cases that the algorithm, they give completely different, not completely, but some of them are really, really different. You go from this one to from 300 to more than 1,000. Okay. So in this case, we have been using the mean, but also using the mean without the minimum maximum. Okay, so is the minimum of 4 value excluding the minimum maximum. In this way, you get a mean that is a bit more robust, and you try to avoid bias. Okay, inside to the model. Anyway, over here there are deep explanation of this algorithm, sensitivity of this algorithm. That are very well explained inside to the video recording. But for now, we are going to use just this one as a mean. What it is? Yes, this one. No, maybe it's not in that file. Is one of these. There is height versus predictors, and where the height is the is just the mean of the 6 algorithms. Okay.
Okay, excluding the minimum.
Minimum maximum, yeah.
Yeah. Okay. Because the JEDI team, they also have their own default algorithm.
Yeah, they have also the default. They I mean, then it's becoming really in according to the deep analysis for making a massive implementation. So I just did it a simple data set that can be used for the class.
Okay.
Yeah.
So it's basically average out of all those different algorithms, the heights, and then this averaged height is used to make wall-to-wall map.
Okay, no, in our case, it's not wall-to-wall map because it's the computation does make is not enough. It's just a little study area in north of Germany.
Yeah. Okay.
Yeah, but the concept is that one. Yes.
Okay. Thanks.
Okay. Cool. Any other question? This aspect. Okay, I think that so if you go back inside to the syllabus, and inside to the syllabus and you click over here, intro to machine learning, you are going to follow up with Antonio presentation and And by the way, Molten, this one is the video that I was mentioned about more deep analysis, more deep understanding of the JEDI data from last year. Okay, so Antonio, the floor to you.
Cool. Let me share my screen.
Yeah, we can see.
Yep.
Perfect.
Great. Let me move this out of the way. Cool, guys. Nice to see you all again. I hope you guys remember me. I'm Antonio. I'm going to be discussing with you guys like some data analysis and more specific machine learning for any type of data, but with like focus on the applications for the geospatial domain. Okay. So this is going to be a shorter class because part of this class was already taken by Pepe to explain the data, right? So I think that right now the overall agenda for the class today is going to have to be a little shorter, but like, let's see how far we get. And that's another thing that I want to say like from the beginning. Please feel free to stop me at any time, right? Because like, it's not because I have an agenda for the class that I have to go through all the points in that class. Most often what happens is that I have to bump part of the content to the next class, right? Which I'm going to explain like in the structure of the classes here. But the goal for today is to tell a little bit about the structure of the class, what I'm envisioning for the next classes after today, right? And a little bit of what I want to do in Matera. I'm going to very briefly like describe the different types of learning, right? Pepe was already hinting to that, like the supervised versus unsupervised type of learning, some frameworks of learning algorithms, and which ones are the ones that we're going to be tackling in this course, okay? And then I'm going to start with the first learning algorithm that probably is like very popular among you guys, which support vector machine. We're going to discuss some of the optimizations and then finally apply that like in a hands-on tutorial. Okay. So what's the structure of the classes in general? So since we're all friends here, right? So like I'm going to always start my class with a quick recap of like what we saw in the previous class. Both like to finish some content that I left behind because that's going to happen, I'm sure. And then also like to address some questions that were remaining since the previous lecture. Okay. So we're going to have time for that. Then we're going to introduce some new content, right? I put 10 minutes of a coffee break. I don't know exactly how much of a break usually we have here, Pepe.
Yeah, 10, 15 minutes according to the lecture, yeah.
Okay, good. Then after the break, more content. I usually put some quiz because it happens quite often as well that like people just don't talk to me, right? So like I don't know exactly like where guys stand with respect to what I just said. So like I usually put some quiz, which it's meant for you guys to assess your own understanding, right? And then based on like these anonymous answers that I get to see like, okay, people are getting this thing right, this thing is wrong, so like probably I should address that again, okay? And then we're always gonna try to finish each one of the classes with a hands-on tutorial, like the last 30 minutes. If you sum all this, you're gonna realize that there is still 15 minutes missing. And this 15 minutes missing, it's like some slack that I give myself, so because I talk too much. And most often like I run out of time, so like that's my slack time there, okay? Very good. So now what I intend to do for the classes. So the first class I already told you what I'm going to be doing today, right? The second class, things start getting more interesting, right? Because then we start getting to like, what's the state of the art in machine learning, right? So we're going to talk about other regression algorithms first, of course, because like not just support vector machine and neural networks, they do regression, but there is like a huge family of like algorithms for regression, as you can imagine. Then we're going to start moving like to more specifics, right? So for example, what means to minimize a loss function, right? Like how do we train these models in general? We're going to discuss like methods for optimization. And then finally, we're going to get to this fundamental unity that builds large neuronal networks, right? And basically is like what was the revolution in deep learning, which is called the perceptron. I'm going to describe that in more details. We're going to start scaling things up. So like we're going to go from the perceptron to like actual neuronal networks. So we're going to start stacking these single units of process, which like the perceptron also you can imagine as like being a single neuron in a neuronal network. Okay, so we're going to start like scaling this up. We're going to motivate exactly when the perceptron starts failing and when we should like start using large neuronal networks. For the fourth class, I'm going to be discussing with you guys like some general rules on how to train the neuronal networks. You're going to realize that there is no like baking formula for like how to make like the optimal neuronal network, but there are some guidelines that's like if you follow, most likely you're going to end up with a neuronal network that does the job that you expect, right? Which includes hyperparameter search. And I'm going to introduce a platform to you guys, which I'm not entirely sure if you already know that or not, which is called Weights and Biases. So it gives you a lot of insights about the models that we're training, right? And since we're going to be training several models, like to see which model, which tweaks of the hyperparameters you do usually lead to the best performance of your method, you need a platform that can organize that for you. And that's Weights and Biases, right? And we're going to have a tutorial just on that. So like probably this section is going to be the one that we're going to spend most time coding together, okay? Then we're going to talk about doing classification or regression and two-dimensional data, right? So like then we're going to move like from the tree height data set to start working with a different data set, which is the satellite images, right? So essentially like we have a bunch of pictures like from satellites that are going to be from different types of like forestry or like urban areas, right? So we're going to learn how we can use convolutional neural networks to extract features that might be predictive of what's the class from which that image belongs, right? So like if it's like corresponds to the desert, if it corresponds to the ocean and so on, which I think is going to be like a valuable study case for you guys. And the last class, right? I did it last year and I think it was quite interesting, right? I call it bring your own paper. Okay, so like how does it work? You guys are gonna most likely you guys have like some machine learning paper in your field, right? That's like doing some data analysis that you would like to be able to understand a little better, right? So I reserved that class for us to discuss these works. So you're gonna say like, oh, Antonio, I saw this cool paper that's using machine learning to make forecast prediction of precipitation in the Amazon, right? And they use this method and I don't understand, right? Because most likely it's going to be a method that we didn't cover in this class. But if that's the case, I'm still going to try to break it down and like introduce you to potentially like a new concept in machine learning. So that's the idea. And with that, I can point you towards more specific resource where you can get more information about that type of work. Okay. Cool. So again, that's the plan. And it all depends on you guys, right? So for example, I can go faster, I can go slower. If you guys say like, oh, you know, Antonio, actually, I think we don't have that much interest in convolutional neural networks. And if the majority of the class agrees, oh, we would rather have the fifth class as being like unsupervised learning. I'm totally cool with that. I can teach like another class just on unsupervised learning. So that's gonna all depend on you guys and what's the feedback that I get from you. Okay, any questions for now? It's okay, 11:36. So we have a break at noon, Pepe? Is that how it works? At noon for my time, sorry.
Whenever you feel needed. I mean,
Okay.
Changing subject is very flexible.
Okay, good. All right. Okay, so maybe we can start here like in a very informal conversation. So I would like to know what you guys think machine learning is, okay? So you see this QR code there. So please go ahead and scan it or use this link that's listed here, okay? And you guys are gonna be redirected to a page where there is a place for you to input what you believe machine learning is. I'm gonna be using this platform all the time because that's also where I'm gonna be running the quiz, right? So please let me know if you have any issues to access this. Right now, the page should be saying that the host is going to activate it, and I'm going to do it right now, okay? If you don't manage to see that, please let me know. It should be active now. And now I wait for the answers to start popping up. I'm going to share the other screen. Okay. So please give me like just one sentence of what you think it's machine learning. Of course, there is no right and wrong at this point. Let's see, kind of like a very complex multivariate stats. Okay. Using algorithms to provide new insights into data. Cool. Observation. Machine learning involves the use of observational training data to make predictions based on statistical models. Ah, that's a very formal definition. Okay. It's a complicated linear regression. Okay. Awesome. Automated pattern recognition. Very cool. The broad set of techniques to get the useful information from big or complex data with no linear methods. So yeah, machine learning can be linear too. So like we're going to discuss that, okay? It's automated pattern recognition that it has some degree of truth to it. Although like machine learning is not just pattern recognition, but like that's a subclass. Complicated linear regression. Yeah, that can be true as well, okay? Let's see, pattern recognition algorithms, they predict based on observational pattern. Excellent, yeah, I think that's pretty good. Train the model with known data to predict the unknown. Okay, yeah, that I think that's in the end of the day, like the big goal, right? Like you want to be able to make predictions for unseen or like new data that you're going to be collecting. Just like as Pepe was mentioning before, that region from which we didn't get data with the satellite, right? We'd like to make prediction for those as well, right? Because it's not that useful to just make predictions where you already have data from, right? So that's very good. Creating data by applying algorithms to related data. Okay, yeah, so that's to be like a more generative aspect, right? So like you learn a lot about a specific type of data, and now you want to replicate data that might be realistic, right? So there is a whole family of algorithms that fall in that class, including like ChatGPT, which probably you guys have heard quite a bit about. Okay, I think that's good. Let me go back to my slides then. Thanks so much for the participation. I'm having a very positive feeling about this class because you guys are very participative people. Very good. Great. So what is my definition of machine learning? Okay. And then you see where your answer falls in that category. So machine learning is the process of identifying patterns in data, right? Which is like, again, that's one very general definition, right? But like that's also encompass how we're going to make use of that data to extrapolate to new regions, like to extrapolate to unseen new data. And with the idea of also gaining insights on which patterns or features or what's the word that you like to use, Pepe? Predictors, right? Which predictors matter the most, right? So like you see that like all of that falls within what we expect to gain in terms of knowledge with respect to machine learning. We are not just predicting building a black box that takes input from one side, takes data from one side, and then just gives you like a final label or like predicts a value for you. But we also want to gain insights about like how the model is doing that, right? Which the interpretability component of machine learning, which is very, very important nowadays, right? You don't just want like an algorithm that says like, oh, in this X-ray that you took, I see that you have a broken bone. Okay, but I have so many bonds in that image. Like, where is the broken bond? Can you identify that for me? So like, it's very important to be able to say exactly where things are. Okay, so like, let's start with like let's go back to like the basics, right? And let's at least get to understand what's the difference between supervised and unsupervised learning. Okay, so like how supervised learning works, like in the most general concept. So like usually we have a bunch of labeled data, right? So like for each one of these entries in my table, for each one of these rows in my table, I have a bunch of features or predictors associated to them. In your case, could be like, what's the latitude, longitude, latitude, what's the elevation where that point was collected, right? Precipitation index and so on. And the label could be something as like, okay, what's the type of vegetation that I'm going to find in that area? Okay, so this vegetation in this case would be what's the label associated to that data point. Okay, so how do we train a supervised model, right? So to make it more general, let's imagine that here we have basically two categories, two classes or labels here in this case, which are essentially a strawberry and bananas, which are represented by the cartoons. Okay, so the training takes place by me inputting this new sample to the algorithm, right? The algorithm is going to try to extract features, learn features, and how to weight these different features from my input data, right? Which features most important, which features are less important, right? So like which features they're just simply noise, and make the best out of those features that are being presented, right? And then I'm gonna count on someone, usually like a human expert, to label those samples so I can use that to fine tune or train my algorithm. Okay, very good. So in this case, sample one, label strawberry. Sample two, that was a banana. Okay, and then we finish building this algorithm, right, with these labels. And in the process of like the algorithm learning from its mistakes, so like I make a prediction, I double check with the ground truth information, which was the label that was given by an expert, right? In this case, I change my weights, or like the way how I weight the features of the data in order to get closer and closer to like what would be the ideal prediction, which is like making no mistakes at all with respect to labeling the samples that I got. Very well. Now, where things go wrong with machine learning. So right now, I'm giving to you what it's, I believe it's a nut. So it would be like, I think that's the nut from the squirrel from the Ice Age cartoon. But so if I give that sample, right, to the supervised learning model that we just trained with bananas and strawberries, what do you think is going to happen?
It's going to tell us that it's either a strawberry or a banana with some confidence.
That's right, because I only have two classes, right? And this algorithm was trying to identify either strawberries or banana. What's going to happen is that I'm going to identify this nut as a strawberry, okay? Which is a mistake. And that's essentially like when you fail in extrapolating or like making predictions for unseen data, right? Can we call that some degree of like overfitting? I don't know if you guys are familiarized with that, but essentially it would stay for like, okay, I can only handle cases that are in this very narrow set of cases, right? So like, which is like, okay, don't come to me with an orange because I have absolutely no idea what to do with that information that you're providing to me, right? So it's a model that generalized very poorly to like, to this problem that would be fruit classification, right? But rather it's a model that's very good at one specific task, which is like separating bananas from strawberries, okay? So for the cases where you might be expected to come across to things that you have never seen before, that's let me say in the first place that's an active area of research in machine learning, right? So like there is no unique or like silver bullet for solving this problem. But there are a couple of things that people have been trying with, right? And they all fall in the category of unsupervised learning, right? So like for those that don't know what's unsupervised learning, So the case is a little different. So now we have a bunch of unlabeled data. So we just have the features, okay? So we don't have labels at all about like what that sample belongs to, right? And then what we have to do is try to come up with algorithm methods that essentially try to organize this data, right? Each one of the samples according to the things that they share in common, right? Which are like, could be the features, right? Or something else that people usually call as like self-supervised learning, which is essentially like, I have a weak guidance of in which direction I would like this model to be going, right? So for example, I know that if I get two samples, right, that they come from a shared space, for example, the space of fruits, the fruits, they should be closer together than, for example, fruits and a nut, right? They belong to a different category, right? And usually they should be clustering different places in space, right? Which is a clustering technique in this case, which is something that we're also going to be discussing in the short feature, okay? So you see that's like when you're talking about unsupervised learning, then you start discussing things such as clustering, right? Because although you don't necessarily know what are the labels, once you embed those samples to a space where all the noise was removed, right? You should start seeing some patterns that usually can tell you not the label, but the degree of organization. So like in this type of space, what you're gonna see is that, for example, if I get a cherry, right, I'm gonna have a representation for cherry. The representation here could be something as simple as like a vector, right? A vector that tells me like what's the degree of affinity for this new sample with respect to the other labels that I have seen before, right? Or simply like taking this sample from the original space, which is like the number of pixels that I have for that image, right? To a low dimensional space. So that's dimensionality reduction. Dimensionality reduction, there are several algorithms that also do that for you. So like takes you like from the original data space. So for example, if its image is the number of pixels that we have, if it's like the tree height data set, that's the number of columns that you have. Those are the features there, right? If we assume that like actually some of this information that I have in the original space, either like number of pixels or the number of columns that I have in this table, they don't mean anything. I just want to keep like the most important information. I can use a dimensionality reduction method to take it from the original space to a low dimensional space, right? So in this case, I have two values that are associated to that sample, right? So now I can compare what's the value that this dimensionality reduction is giving to me, right? So for example, now I see that the cherry has a value 0.7, 0.5. This seems to be a tomato, 0.2, 0.1, right? Now I get this other type of berry here, and the output for this berry was 0.6, 0.7, right? If I keep doing that with enough samples, you're going to start seeing that like the vector representation, right, after the dimensionality reduction from the original space to this low dimensional space, they actually start to show some degree of clustering in terms of like what's this vector representation. So you see that, for example, this 0.6, 0.7 is closer to the other cherry, right? 0.7, 0.5, than to the other fruits that I got as input, right? Which here's a tomato, and these other two I have absolutely no idea what these fruits are supposed to be, but that's what like the Microsoft Word gave to me like in the category of fruits. But that's essentially like just showing that they share more things in common, right, than the two berries. Which factors you believe are the ones that are mattering the most for me to separate those two potentially classes that we have in this data set? Can you pick any type of like features here that might be determining the clustering that you're observing?
You mean features from the graphics or the features from the numbers?
No, from the graphics. So like the features from the numbers, they're coming from like this dimensionality reduction or like feature extraction, right? That it's coming from the original domain, which is the image, right? But in the image domain, which things you believe are the ones that are being more deterministic in terms of like finding this vector representation that you're finding? what's perhaps like the aspects or characteristics of this image that seems to be clustering them?
So
And again, like we haven't trained any model here, so like just things that you believe could be driving this type of like separation that you're seeing.
So the other fruits have some leaves with them and they tend to be smaller, and the top set of fruits are all round and they are like one thing, whereas whatever it is on the bottom, there's two things and there's leaves.
Absolutely, yeah, you nailed it. Anybody else wants to add anything to that? Fernanda said shapes and dots. Okay, yeah, those are like some features as well, for sure. Anything else that anyone would like to add to it? Complexity or size. Complex is hard to define, but size could be one of them, right? Although, like, for example, a tomato, it's hard to compare what's the tomato size with respect to what's the berry size, right? Because they are not to scale. So like I would have to give you more information. So like all the images they were taken with 1:1 scale, right? So like the image actually contains the actual fruit size in the same basis for all the images, which I didn't provide that information. So sizes, it's difficult unless I provide more information to you. But those are all great answers. I think there was one more. The seeds, okay, yeah. Although I don't have seeds for the tomato, if that's what you're describing there, but like, yeah, I don't have information about seeds for all the images either. But yeah, so, but I think we got like a good point here, which essentially is what this vector representation usually is codifying, right? Which could be anything that we are extracting or like learning from the original data domain, right? Again, I hope these concepts become very clear. So when I'm talking about the data domain, that would be the domain where the data lives, right? So like in this case, the pixels in the images here, right? Which is like this image that we're observing, okay? In the tree height data set, those would be the X and Y, all the other information that comes from the satellite and the other layers that usually we aggregate for like including more information, right? I hope that's clear, but are there any questions with respect to that? Okay, so let's just summarize like what's supervised learning and what's unsupervised learning. So we had discussed that like in supervised learning, we have a bunch of labeled data and we want to label new data after that, right? So like after I have collected all these images from strawberries and bananas, right, for example, now, when I get exposed to a new image of either strawberry or banana, right, I want to be able to classify them with like a high degree of accuracy, right? So that's essentially what the supervised learning framework offers to me. And that stands for like, now I have a function, right? I'm going to start introducing some mathematical terms like little by little, very, very gentle, okay? So now I have a function that takes like a new input, a new data, X, right? And I'm going to map those features from X to a label that's part of my dictionary of labels or classes, okay, which is Y, right? So that's a simple function F that receives X and maps it to Y, okay? Very good. So now in the unsupervised learning case, we have a bunch of unlabeled data, and all we want to do is to be able to find a degree of organization to it, right? Like try to learn a representation where this unlabeled data, it starts to show some structure, right? And like potentially get separated, and it facilitates to me like to identify which things are more similar to each other than others, okay? So like that was the idea between like rounded shapes like fruits, right? From the berries that had leaves and like small circles on it, okay? And in that case, we also learn a function that's considered F that receives X, right? Where X, again, are the input features. It maps it to Y. But look that Y is no longer a label, right? And in fact, Y is also multidimensional, right? Here we had a Y that was corresponding to just like a label. So like that's just like a 1D vector, right? Now I have y that can live in a space of dimension m, right? So for example, in this example that we had here, we're mapping pixels to a 2D space. So m was equal to 2, okay? But I can map it to like a higher complex, a higher dimensional space. Just that most likely what to do is to take it from the original space. So like, let's say that's n, was an image, for example, of 64 pixels by 64 pixels, right? So that's a space of 64 times 64. And I want to map that to m that's much smaller than the original space, right? So like we map it like from the 64 by 64 image to a 2D space. So like the n tends to be much bigger than m, with the hope that in the process of learning how to extract features from this data that we're working with, we're gonna get rid of all the noise, all the things that don't matter, like the white background in this image that you can observe here, right? And just keep like what really matters for me to be able to classify or cluster these images, okay? Any questions on that so far? So far we have only discussed definitions, right? And we have been talking about these hypothetical models that takes like the input data to either a label or like a vector representation, okay? Questions? Okay, if there are no questions.
Sorry.
Yeah, please.
Ask, like, for example, if you are building a regression model, then that's supervised learning, right? Like if you are just getting a precipitation and then using precipitation climate and predict the tree height, and that soil to predict the tree height, that is supervised learning.
Correct, yeah. So for example, if I'm taking this, I think that you said that you wanted to predict like 3 things. Is that what you mentioned there?
Like just like an example, if we use like a climate, precipitation, soil moisture to predict the tree height of the location, that is a classic supervised learning.
Absolutely, yeah. And most often, if you're trying to build to predict something that's a real number, which in this case would be a real number for numbers greater than 0, right? Which is the physical height of the trees, right? What we're talking about is a regression, right? And our regression implies that you have information, ground truth information about the system that we're modeling, which in the case is the actual measured height of the trees, right? So if I have real information about the system that I'm trying to model, that's supervised learning.
Okay. May I
Because
ask,
I'm trying
what is the, sorry. May I ask, what is the, then the, like an environmental actual application of an unsupervised learning?
Yeah, so for example, let's say that I want to, okay, I give to you several samples that are coming from images that for which I have no label at all. Okay, so for example, let's think of like the satellite images data set, right? So those are like aerial spatial pictures that I have. For each one of these pictures, I don't give you the label, right? But you know that, for example, from looking at them, you're going to have some pictures that have forests on them. You're going to have some pictures that are just taken like from the ocean, right? If I take those images and I embed them to a lower dimensional space, what I'm going to see is that in this lower dimensional space, I'm going to have like a cluster of pictures that they sort of correspond to like homogeneous blue background, which are ocean. Okay, so like I don't have any label. I'm not trying to approximate the label of those images that I got, right? Because if I was trying to find, okay, simply find me a way to separate those classes, right? I would be in a supervised learning framework, right? On the other hand, what I'm doing is just trying to find a representation, right? A lower dimensional representation that includes a easier way of separating classes. You see, so like this low dimensional space is going to give me just like a set of points that are organized according to like to the way how I extracted features from the input space. After I have done that, right, Now I can come with like someone that knows better about the data and say like, oh, actually this cluster that I have here, it better recapitulates the image that came from ocean. Okay, so like image that came from ocean. Now, for example, let's say that I got like a bunch of pictures that come from forest, right? The actual label was just forest, but if I look in closer details to the forest cluster, I might see that's like an actual, I have different types of forest like image within what I was considering initially as being just forest. So I have like the Atlantic forest, I have forests of like drier regions, you see? So like sometimes you gain more by using unsupervised learning, because then you just like clustering things that are more similar to each other, right? Completely unrelated from label. Is that clear?
Yeah. So sometimes it gives more insight than original label. I mean,
Right. Yeah.
original
Depending on the
classification.
algorithm that you're using. Yeah.
Okay. Cool. Thank you.
Yeah. Because like if you train it as supervised learning, it's gonna get as good as the test that you're defining, right? So like we know that we have several types of forest, right? Like forest is a pretty broad definition, right? But we can tell them apart. But like the label that I got, that I give to you to train a model is just forest. So like all these things going to be able to tell apart is like if there is green or not in the image, right? And you might be interested, like try to understand something more deep about like the different class categories of image that you have in the data set.
Okay, great. Thank you.
Hello,
Yeah.
Anthony.
Any other
Anthony.
question?
Hello.
Hey, hi.
Okay. So in a layman language, unsupervised learning is like grouping.
So let me repeat the question. So you're saying like unsupervised learning is equal to grouping?
It's like, oh yes, grouping, unsupervised learning. By bringing them into low dimension, it's like grouping. Okay.
So yeah, grouping or clustering. Clustering is the you can assume that like grouping or clustering, they are equivalent in this case, right? And like the clustering usually happens as unsupervised, right? So like, for example, I don't know if you guys have heard of k-means, for example, right? So you get the data. Okay, great. Yeah. So like you get the data from the original space, right? And what you do is use an algorithm that's essentially just saying like, okay, assume that I have K categories here, right? But I give you no information about which categories they are. I just have like 5 categories. So like split this data for me in order for me to get 5 different clusters, right? And then what this algorithm is going to do is try to leverage the information that's coming from the features, right? In order to place each one of the samples in one of the 5 categories, right? So yeah, so you see that like I had no predefined labels, but I did have to specify the number of clusters. But yeah, if I don't have labels, that's unsupervised learning.
Okay.
Okay.
I have a question.
Yeah.
In the unsupervised learning, are we the ones to tell the machine this is the number of clusters I want, or it automatically generates the clusters?
That's a great question, if I understood it correct. So I'm going to repeat just to make sure I got it right. So you're saying that you're asking if there are algorithms that don't take the number of clusters as input. Is that the question?
Yes. Yes.
Great. Yeah, no, that's an excellent question, right? Because if you have to define the number of the clusters that you expect to find, you're biasing your analysis towards like the number of clusters that I was expecting to find, right? So for example, bring it back to the example of satellite images that I was mentioning earlier, right? If I say that like the truth labels that I had, right? They were ocean, desert, like forest. Let's keep to these 3, right? If I say I want to find 3 clusters, this k-means algorithm is going to find a cluster that most likely is going to correspond to ocean, then desert, and finally forest, right? But now if I say, no, actually I want 10 clusters, right? okay, ocean most likely is going to keep being just one single cluster because it's very stereotypical, right? Like we only have like water, right? Desert most likely is going to keep being as one single cluster, but forest, as we were saying before, I can break forest in different types of subcategories, right? So like I have very dense forests. I have forests that are a little bit more scattered, right? I have forests that have slightly different tones of green. So like I'm gonna break all these big category forests in several subgroups, but it still is biased by the number of clusters that I'm giving, right? So there are several unsupervised learning algorithms that they don't take the number of clusters at all, right? So like essentially what's going to do is to find what's the optimal way of separating this data according to the features that you're giving. But there is, if you look closely, there is always some sort of bias that you have to insert in these algorithms, which I'm going to refrain from digging too deep in there. So for the sake of time, but like you can assume that most often there is some information that you need to provide for, even for the unsupervised learning algorithms, that's going to bake in some assumptions that you have about the data. But yeah, there are workarounds. Yeah.
Okay, thank you.
Okay, any other questions? So it's 12:07. Okay, I just wanted to go over like the learning algorithms before we go for a break. Okay, so bear with me for a little longer. So now that we have discussed very briefly, like what is the difference between like supervised and unsupervised algorithms, right? Let's try to step back and like come up with a more general definition, okay? So if you look at the cookbooks of like machine learning, right, it can be boiled down to a sentence that basically reads as the following, okay? So a learning algorithm is a computer program and it's said to learn from an experience E, okay, with respect to some class of tasks T and performance measure P, okay? And if its performance at task in T as measured P improves with experience E, okay? So now let's see what we can use to replace these E, T's, and P's that we just saw there, okay? So among the tasks, okay, so we have been talking a lot about regression, for example, right? So now let's replace the T in this sentence above as regression, okay? So assume that I want to do a regression. A computer program is said to learn from experience E, okay? So like from the list of experiences, right? If I want to do a regression, what type of experience do I have to select? So the experience essentially tells me what's the type of labeling that I'm going to be using, right? If I want to do a regression, I had to do a regression with respect to a ground truth information, okay? So if I have ground truth information, I'm in which type of experience? Supervised learning. Excellent, right. So a computer program is decided to learn from experience E, which is supervised learning with respect to some task of T, in performance measure P. Okay, very good. So now if I want to train a supervised learning algorithm to do regression, I need to define what's the correct way of like measuring the performance of this method. Okay, so like by performance, we have a couple of options, right? Which I didn't list all of them here, of course, right? But when you're talking about regression, most often what you do is like, okay, I have the actual value that I would like to be predicting, and I have the output from my model, right? So what's the easiest way for me to make an assessment of how well my model is doing? Is by either computing the mean square error that I have, right? So like how off I am from my prediction, right? Or mean absolute error, like all these metrics, they try to measure the same thing, right? Which is like how far off I am with respect to my prediction, right? Or you can use the R-square. So like for each point that I have, right, in my data, I give you like an output, and then I compare that to like what's the ground truth overall. So like the highest the R-square, highest is the similarity between my model output and what's the ground truth information that I have, okay? The same can be applied for like other types of tasks, right? But you see that like, for example, if I go for anomaly detection, right? So like anomaly detection being like the simplest case, which is like I'm modeling, let's say, the usage of credit card by one specific client that I have in my bank, right? I don't know the full set of possibilities of fraud, things that can go wrong with respect to someone like cloning the credit card or like simply like stealing the information from that client. So I don't have an actual label for like all the potential things that can happen, but I can model the behavior of my client in the type of purchase that he makes, right? So like I see that usually he spends money like buying lunch, and then like later in the afternoon there is a coffee break. He travels like twice a year, this kind of thing. But suddenly I have a bunch of purchases that were made on Amazon, like some MacBooks, you know, something like that. So I see that there is a deviation from the normal, right? But I don't have actual labels for it. All I'm doing is like detecting that there is a deviation from the normality, right? What type of learning, what type of experience you think would basically describe this type of task?
The anomaly detection?
Yeah, normally the detection is the task. So like what type of experience I would have to select?
Unsupervised?
Unsupervised learning, very good. Which kind of metrics you think I could use for that?
Accuracy rate?
Could be an accuracy rate. Yeah, so like I don't have an actual information about when these things happens, right? But after it has happened, I can say like, okay, this was actually correct. So this was the detection of some sort of fraud. Okay. Any questions here? Can you guys think of any other example? Like bring a problem that you work on, and then we're going to try to place this problem that we'll work on, problem being like a task in this case, and we're going to find like what's the good performance metric P and experience that basically describes the problem. Anyone?
I'm sorry, could I ask a question about the previous example?
Yeah, of course.
I'm still not, I didn't understand properly about how do you get the accuracy rate for an unsupervised learning?
Yeah, so for example, the accuracy rate in this case would be like, how often do I manage to get something right, but after it has happened, right? So like I have an expert that's just gonna say like, okay, back then I managed to identify that fraud like with this degree of like accuracy, right? But I didn't classify the type of fraud per se, right? So that would be like a post hoc inference of how the model was training. Okay.
Okay. Yeah.
So
you're judging the performance of the model, but you're not really training the model based on the accuracy.
I'm not training the model to predict specific labels, right? So I'm not saying train the model to like, okay, here is what you should be predicting. So all I got is essentially like there was some abnormality in the behavior of this client. You see? So like I'm not fine-tuning this model towards identifying a specific type of fraud, right? But rather like extracting meaningful information about the behavior of the client and give me an estimate of potential points of fraud there.
Okay. Yeah, all right. Yeah, now I got that. Thank you.
So in fact, you're detecting something like outliers, yeah, in the model behavior.
Yeah, detecting outliers, yeah. Okay. All right, so we have discussed a couple of things so far, right? So like, and also I have shown to you guys this diagram before, right? So like within this big umbrella of machine learning, right? We can start by dividing all these learning algorithms in three main categories, right? So it'd be like supervised learning, which is the one that I believe that Pepe says that's the one that's most used, like in geospatial data, right? Within supervised learning, you have classification, right? So like, for example, he was talking about decision trees, in random forest. So like those are very popular algorithms, which implies that we have some sort of labels to work with, right? Which in this case, they are like categories. We have been talking about the example for the satellite image. That's the type of like supervised learning where you're going to be trying to regress the label, or like what's the category of the image, okay? And of course, you can do that with neuronal networks as well. In regression, you can use something as simple as a linear regression, right? Who here would say that linear regression is machine learning?
I mean, based on the
Most
definition we
people-
just heard before, it is, no?
It
Kind
is,
of.
yeah.
It is.
So there is actually like this very funny meme on Twitter that says like, tell me when was the first time that you realized that machine learning is pretty much just linear regression. Because you're gonna see that like the way how we optimize things, of course, they have to be like scaled up to deal with like very large models, right? But in the end of the day, they are all trying to perform some sort of linear regression. And that's why I'm gonna be discussing like linear regression in more detail, so we can start tracing these parallels, right? So you realize that like doing machine learning is not that complicated after all, okay? There are some intricacies with respect to like how to train such big models, but like in the end of the day, they're not very different, right? Decision trees can be used for regression as well. So like that's, for example, the random forest that Pepe was going to show you guys. We're going to be discussing supported vector regression in a little bit, right? From unsupervised learning, we already touched very briefly on k-means, right? So like that's where you don't have actual labels, right? But you say how many clusters you expect to find. But like because you're not trying to optimize your model, right? To place each one of these samples in a specific category, you're just trying to separate them according to some metric of similarity, right? That's considered unsupervised. Okay, so for example, like hierarchical clustering as well, that's another type of clustering, right? What else? That's not machine learning, is not neuronal network oriented. Well, let's just stick with those two. And reinforcement learning, I'm going to skip because that's like the most meaningful for you guys right now. Okay, but like again, right, we are talking about like supervised learning, which includes regression, right? In this example, the case that you actually can deploy such techniques as supervised learning, it's a very small subset of like the problems that probably you guys are going to have to face in the wild, right? Because like collecting data that has labels associated to it usually is expensive, right? Because, for example, for the satellite, for the tree height data set, right? You guys need to deploy people to the field to actually measure what's the height of the tree that you made a prediction about, right? Otherwise, all you have is like all the satellite image and so on, right? But for you to have an actual ground truth, like what's the true height of these trees, you have to deploy someone to the field to go and measure each one of the trees, like or like a subset of trees in that region, right? So like that's expensive. Like when you're talking about medical image, you have to pay actual medical doctors to say like, okay, so here are the cancerogenous cells that you should be able to identify, or here's like a broken bone that you have to detect, right? So you have to spend a lot of money for that. And the bulk of the problems actually correspond to unsupervised learning problems, where all you want to do is to gain some insights about the data, right? So like, I want to understand, I want to make sense or like extract meaningful features that might be, that might help me to understand better the problem that I have in hands, right? So like, that's most of the problems, but like for the sake of time, you're going to stick to the supervised learning methods. And if you guys have more interest on the unsupervised direction, I can point you to more resources or even like teach one class in the Wikimatter or so on. Okay, enough of me talking. Let's do a fun quiz now. So please go back to this link. Or should we take a break? Probably we should take a break, right? We have been here for like 1 hour and 20, right? So let's do the following. I'm gonna please log to this link, and then after the break in 10 minutes, we're gonna play with the quiz. Okay? Does it sound good?
That's good.
Perfect. We will come back
Okay.
at 35.
Right, yeah. And then like during this quiz, we see like what needs to be readdressed and come back with your questions as well. Okay, cool. See you guys in a little bit.
Thank you.
Okay, so we can resume.
All right. So is everyone here? If you're
Yeah.
not here, say something.
Yeah.
Yeah.
Yeah, I think there are quite everybody. Yeah, okay.
Right. Yeah, good. So, okay, so little quiz, okay? And because we're kind of like running late, let's try to make it like rapid fire, right? So what I'm gonna do is like, I'm gonna activate the first question. I'm gonna leave it open for like 10 seconds. And you guys answer it, and then I see the answers, okay? Is everyone ready? Like, do you need the QR code again?
It's
It's
Yeah,
the
because
same
of-
link, right?
uh,
We just leave the voucher.
Yeah, because for me the old QR code leads me to the former like question, what is machine learning, and I cannot open the quiz with it and don't know, maybe it's common problem.
Okay, now I'm gonna activate. Is it active now?
Yes.
Maybe
See what's the, okay, hold on. I'm gonna move to the previous question.
Yeah, yes,
maybe-
now
What's the second?
now it looks like
yeah, post
Okay,
the
yeah.
link.
now okay.
What's machine learning? You should be able to see it now.
Yeah.
If you don't see, I can post the link very quickly.
Maybe in the
Let me
chat.
post the link. Yeah, I'm gonna put in the chat as well. And in the meantime, please answer the question. Where is the chat? Oh, here. Found this. Okay. So you should have it there. Okay, I have 10 answers. I need 15 answers. We are 20 people, right? If I remember correctly. Okay, 11. Okay, that's good enough. Okay, let's take a look. All right. So everyone thinks that the process of training a model to perform a task using data and statistical algorithms. Okay, no doubts at all about that one. Excellent. So since you have no questions on this, let's move to the next one. Activate. Okay, so what are the three main types of machine learning? Okay, one more. Are we 14 or 15? For some reason, I thought we were 15 people. Anyways, let's move on then. So 86% of the people believe that supervised and unsupervised reinforcement learning. So, and 14% thinks it's supervised, unsupervised, and deep learning. Okay. So I hope this was clear from the diagram that we had, right? So like we had supervised, unsupervised, and reinforcement learning, right? In fact, deep learning basically is just talking about how complex is the model. So like you can have deep learning for all the three. You can have deep learning for supervised learning, for unsupervised, and for reinforcement. So like deep learning per se is not a type of machine learning. Okay. Any questions about that? If not, feel free to drop questions later on as well. But for now, let's move on. So what is supervised learning? Okay. This one people are answering way faster, so I assume that we're not going to have problems with this one too. Now I got 20 answers. How many people are we? Okay.
23. So we should get 20 people. Everybody try to reply, even if it's wrong.
Yeah, even if it's wrong, it's just like it's an assessment for you, like, and also for me to see if there is anything that needs to be addressed. Okay. So like what's supervised learning? So like the majority believes that is a machine, when a machine learns from data that is labeled. Okay. Okay, I see some people changing their minds. Okay, yeah. So I hope this is clear, right? So like when it's unlabeled data, that's not supervised, because to be supervised, that means that you have ground truth data, right? Which is like the, I think someone sent a message here. Okay, so someone is asking, why is not C, right? So to be C, it's basically like feedback provided by the human. The feedback is not necessarily labeled, right? The feedback could be just like, this is good, this is bad, right? And basically that is the concept that's behind reinforcement learning, right? So like the type of feedback, if the feedback is labeled, right? So like, okay, this should be this specific label here, right? And I'm trying to optimize the method to approximate the label, then it's supervised learning, okay? So like depend a lot on the type of feedback that's being given. Okay, great. So next question. Okay, so I kind of answered that already, but let's see. Please go ahead on this one. What is unsupervised learning? Okay, meets the threshold. So let's see. When machine learns, the machine learns from data that's not labeled. Okay, I see that someone voted for B. Oh, changed their mind. Okay, so no need to address this one, I guess. So like, is that clear for everyone? So like, if there is no date, no label involved, we call that unsupervised learning. Okay. So I think I have just one last question. So please go ahead. So this one is, what is the difference between classification and regression? Are you answering too, Pepe? No? Okay.
If not, they bias the result.
Good. 16 people. Okay, that's good. All right. So what's the difference between classification and regression? So the majority thinks is the classification. Classification is when the output is a discrete value, and regression is when the output is continuous value. Good. And that's the correct answer. But someone thinks that there is no difference between classification and regression, right? So actually there is, right? Which is like classification, you're talking about approximating a label, right? So a label, which is like a tree, or like this is a car, this corresponds to urban areas, right? Those are labels. And it matters a lot when you're talking about, for example, the type of loss function that you're going to use, right? Like how you're going to compute the performance of the method, right? So for example, when you're computing the performance of the method for labels, you cannot use root mean square, for example, right? Or R square. It's hard to use this type of metrics, unless, of course, you can use like a trick. For example, each one of these labels, these categories that I have, I'm going to assign them to an integer, for example. So like 3 is now 1. Like a car is 2, and so on, right? So you can use this translation, but you see that you're moving from categories, labels, to a number, which then is already becomes like a value, right? So like, I hope this is clear. All right. And then, okay, so that's it for now. Let's move on. Any questions? Anything that you think is should be better addressed? Any pending question with respect to the quiz or like to the class? In the meantime, I'm gonna open my slides again.
Hello.
Hey.
I have a big problem with the definition of classification and regression. When you say discrete, there are some regression that you can do with discrete value as well.
You can do regression with discrete labels. That's what you're saying?
I am just saying that there are some regression analysis you can do with discrete value as well.
No, you can change the type of labels that you have from being discrete to values, right? And therefore you can say that then it becomes a regression problem. But you see that I'm translating the labels, the categories that I have to the continuous domain, right? Which although is integer, but you can consider that the integers, they still correspond to continuous values, right? Then you can use regression if you want. But when it's a classification, it's better if you use the proper metrics, right? And the proper loss functions, how you compute the error, so you can train your method more effectively. So classifications implies that you have labels, categories, and you should treat as such. If you have continuous values, right? So temperature, or if you're talking about the tree height, right? All these things, you should treat them as regression. Okay?
Exactly. Yeah.
All right.
And I have also a question. We have been shown these three categories, like supervised and unsupervised and reinforced learning. And while about this first two categories, it's more or less clear, even as we've seen on the quiz results. But could you tell a few maybe words about this third category, like reinforcement learning? What is this, and why it is so specific?
Yeah, so the reinforcement learning, right? Although most people believe that that's most likely going to be the way for general artificial intelligence, right? It's the secret is that we don't have labels for everything. For example, when you're growing, right, you don't have a label for everything as you're being exposed to it, right? And therefore, algorithms shouldn't have to learn from labeled data because it's expensive, right? And that's simply not the way how what we consider as being the best way of learning, which is how humans learn, takes place, right? The way how it works is usually we interact with the environment, you get feedback from the environment, and you learn from the experience, right? So for example, when you're dealing, let's say that people in robotics, they're using reinforcement learning a lot. So let's think of robotics, for example. I could train the robots that are playing soccer, for example, to simply score as many goals as possible, right? But you see that scoring goals in soccer implies several other things, which is the quality of the pass of the ball, right? Because if you're just trying to minimize, optimize the task in terms of number of goals, that's too hard because there are several other things that needs to take place, right? But you can give a positive feedback for each one of the actions that leads to a goal, right? So how good was the pass that you gave? For example, how the quality of the interception when the adversary has the ball, right? So each one of those things, they can give a thumbs up or a thumbs down, right? And say okay, keep doing more of these, you're doing right? I'm not saying that what you should do exactly. I'm just saying that, oh, what you just did, this is good, keep doing that, you see? So that would be reinforcement learning. So you see that I don't have labels for it. It's just a matter of feedback. Is that clear? Now, reinforcement learning for geospatial data, I would have to think more about it. I'm not entirely sure where we could potentially find something. Pepe, do you have any insights? Yeah.
Not really. I was also thinking in what context we could use it. Never saw.
Yeah, I see reinforcement learning a lot for robotics, but honestly, that's the only case.
They learn by the mistake.
Yeah, from experience, right? You don't have artificial learning algorithms just a software doing that on its own, right? You could potentially say that reinforcement learning could be used for anomaly detection too, right? So as we were saying before, right? Instead of saying oh, this was a fraud, right? I could give a feedback on this was not a fraud, but good job in detecting this abnormal behavior. So keep doing that. Keep bringing cases like this to my attention, you see? So that could be potentially reinforcement learning there as well.
Yeah.
Okay.
Okay, Alex, you will search for some example in geoscience.
Yeah, okay, okay. Thank you.
Oh, yeah, that's a good question. Indeed. I completely skipped like reinforcement learning exactly because I don't see many cases like for geospatial data. So like I don't know how useful it would be for you guys, but yeah. Okay, so now we're gonna move on to talk about hyperplanes and decision boundaries, which are all key concepts of like supported vector machine, which I hope you guys remember. Supported vector machine, it's one of the branches for like supervised learning. Okay, both for classification and regression. And I'm going to be talking a little bit about all of them. Okay, so like let's think of like a very simple case, right? In 2D, because we're all friends here. So like let's make things easy first, right? So like I have basically like these two data sets, which corresponds to red circles, right? And I have the blue squares. Okay, so I want to find a way to separate them. Okay, so I'm going to give to you the task of finding a way to separate them using a decision boundary, which corresponds here to these blue lines. Okay, so I want you to go back to that link that we have, right? And tell me what's the correct decision boundary for the problem. So again, the problem is I would like to separate blue squares from red circles, and I want you to tell me what's the correct decision boundary for this problem. And oh, I need to activate the thing, so let me activate that. So you guys should be able to see the problem now. If you don't, please let me know. Okay, I have two answers already. I need to share that screen. Okay, when I get 15 people that already has voted, then we discuss the results.
Can you share? Sorry, can you share this QR code once more, because it's not.
It's in the chat. It's in the chat.
It's in the chat, the link as well. Okay, 5 more people, please. If you haven't voted yet, like remember that there is no points for these tasks yet, but actually I could be recording the answers, which I'm not doing, so I could share with you guys later. But like this is for now.
Someone was asking for that in the chat as well.
Oh, really? Okay. Yeah, I can share the right answers with you guys later. I can transcribe this to like a document and share the questions and the answers. Okay, one more person, please, to vote. If you haven't, oh, it was 14, went to 13, 16, perfect. Okay, so like response. So again, what's the question, right? Because the question matters a lot. What's the correct decision boundary for the classification problems shown below, right? So the majority believes it's C. Could someone who voted C please tell me why you think it's C?
I didn't vote C, but I was thinking about it. I think it's because like it's the furthest away from both clusters. So if a new point would appear, like you could argue maybe it makes again the correct choice. But I did choose E because I think for this specific data set, they seem very the same.
Right, right. No, you're absolutely right. And in fact, the right answer here, which like for the question, was the correct decision boundary. It's all the above, right? And why did you choose all the above? Could you comment on that?
They all have perfect accuracy for this specific small task.
Perfect. But as you very well put, like it's not optimal, right? Like you can say that A and D, for example, they are in the extremes, right? If you have a new data point that comes to this space, right? To this space, I have a higher likelihood of misclassifying that point because of the position of the decision boundary, right? So like they are not optimal, but they do classify correctly, right? Now we're gonna see like, okay, so what characterizes a good decision boundary? And I think you have a pretty good intuition already, which was your comment on the C, right? So let's go back there. And I'm very happy that you guys already have such intuition. I need to make this transition between slides faster. Can you guys see my slides again?
Yes.
Okay, perfect. Yeah. So very well. Yeah. So like we have been talking about like these decision boundaries, all of them on the left panel here, they all correspond to like perfect accuracy for like classifying the two data sets here, right? But as my friend Martin, right? He just described to us, they're not optimal, right? So what characterizes optimal hyperplan? Okay, so like let me first say like that the hyperplan in this case, right, corresponds to this simple line. Why am I calling a line a hyperplan? Okay, so the idea of the hyperplan is that this is a decision boundary that can happen in like a multidimensional space. Okay, and therefore that's why I say that's like it's an n-dimensional space. Okay, which is conditioned by the dimensionality of the data that we're working with. Okay, and most often what you see is that these decision boundaries, these hyperplans, they have dimensionality n-1. So for example, here we have a 2D problem, right? So like we see that we have the y and the x, right? For me to be able to classify those, I need a hyperplan that has dimensionality n-1. So like I have 2 for the data set, -1. So I just need one dimension, which is a line, okay? If this problem was living in a 5D space, what's the dimensionality of the hyperplan that I need?
40.
I think I said 5, right? It was like 5D space. So I just need 4 dimensions to create a effective hyperplan. Okay? You guys see the logic?
Yes.
If not,
that's
like
that's what I said. Maybe it didn't.
Oh, okay. Yeah, maybe I misheard them. Okay, good. But if that's what you said, it's perfect. Okay. So now, and that's essentially what we see here as the optimal hyperplan, right? What qualifies the hyperplan as being optimal? Okay. I should have put this in here, but yeah, anyways, yeah. So what qualifies the hyperplan as being optimal, right? The hyperplan being optimal is the one that has the most support from the data points that I'm trying to separate, okay? And where the support is coming from. So like the supports are characterized by these vectors, right? That they try to touch as many points as I can while I'm trying to set these boundaries, right? So for example, you see that the vector that's defining this lower boundary here is supported by those 2 points here, okay? When I have 2 points, I have a line, right? And a line essentially describes a vector. So you see the vector is supporting this hyperplan, this decision boundary, and therefore support vector machine. So it's not a very original name, but it's meant to be intuitive, right? Very good. So now we have like some other key components to it, right? So in the process of doing that, in trying to set where this boundary is, essentially we have like a very clear optimization problem that we're trying to solve, which is to find the maximum support that we can when trying to place this hyperplan. And this maximum support essentially stands for like finding the combination of support vectors, right? That maximize this distance with the maximum margin, right? So I hope you can have the intuition to realize that the bigger the margin that I have, right? More room for like incorporating new data and still having a good performance in classifying I have, right? So for example, let's go to this example. As we saw before, so that would be one of the decision boundaries that we saw before, right? If I have a hyperplan that's in this position, right? Right here shown in blue, right? The hyperplane is positioned exactly halfway between the two supporting vectors that are in red, okay? Here I have a lower margin, right? I'm trying to maximize the margin, which is like essentially I just need to rotate this hyperplane a little bit, right? And I have the maximum support. So here I have like these 2 points that are creating a robust vector, right? And I have these other 3 points that are supporting this decision boundary. So you see that like as many points I managed to touch with these supporting vectors, greatest usually is the margin that I get, okay? Which are all things that like we all managed to have an intuition on, as like you saw, like the majority of the people already managed to abstract that like the biggest the margin, right? Better is gonna be the placement of this hyperplan, and more robust the classifier is gonna be. Is it clear to some extent? Are there any questions with respect to the logic of like how we're trying to place this hyperplan before we get into the math of how to make it happen?
Yes, I have a small question. That's what should form the support of this vector? Either it should be only one point from both sides, from each side, or it should be, for example, 2 points on one of the sides, like on this your picture.
Right. So like you see that like the supporting vectors, they have to run parallel to each other. Okay. So like, because they have to be parallel, what we're trying to do is finding like maximum support in either one side of the data, in the blue side here, or the red side, right? But in theory, as many points I manage to get in that vector that I'm tracing for the support, the better, right? Because that means that like the margins, they are basically touching the points, right? And if they are touching as many points as they can, right? So the distance between this margin here, the support and the data, as close as I can, so like the shortest the distance that I have there, further away they're going to be from my hyperplan. That's the one that's actually the physical decision boundary. You see? So like the logic is like the more points I'm getting, the more points I'm touching, more robust is this support vector that I have, and therefore better place is my hyperplan. Does it answer your question?
Yeah, so logic is to find the maximum possible number of points from either side without like crossing any of the points, if I understood it correctly.
Right, yeah. That could be the rationale. But you see that what we're trying to optimize, it's actually like this, let's get to the optimization, okay? So like essentially, now we have this like formula here that describes how the optimization takes place, right? So how do we go about trying to optimize this thing, right? So we're going to be using this thing that we call the hinge loss, right? So the hinge loss is very simple, right? So let's say that, let me try to activate this. Okay, so like for the example that we just saw, right? Let's say that the points, the X points here, they correspond to value 1. Okay, and then I have circles on this side that they correspond to value -1. Okay, so those are ground truth. So like that's the actual label. So all these points in this side, they belong to the class 1. Okay, and all the points in this other side, like the circles, they correspond to class -1. Okay, very well. So what does it entail? That means that like here, the output of my model, which is f of x, right? If the f of x is equal to 1, for example, so like I am predicting that's going to be an x, right? And the ground truth, which I'm going to call it the y, it's also equal to 1, right? The product of y and f of x is equal to 1. Therefore, the loss is 1 minus 1, which is 0. So like that means that I classified it correctly. You see? Very well. If it was the other way around, so let's say that like the output of my model was f of x equal -1, but the ground truth value -1 was y equal to 1. Then this product, it's equal to -1 now, right? Therefore, this is going to be 1 minus -1, which is 2. Okay, so the loss goes up. So you see that what we're trying to do is to get the maximum agreement between the model output, which is f of x, and the ground truth label, which is y. Is that clear for everyone? Great, yeah. Very well. So like now you see that like this loss function, this hinge loss function is being translated to something that we are going to be using to train the SVM. right? So you see that this is the component of the loss that incorporates the summation of like how we are performing for each one of these points that we're trying to classify. Okay, so how does it work? So here I'm gonna use like some concepts of like linear algebra. And if you have any issues with that, please let me know and I can point you towards like more specific resource. But this here, we call it a dot product between two vectors, right? So W corresponds to the normal vector. Is the normal vector of the decision boundary. Okay. So let's say that the decision boundary here, it's placed in this region. Okay. Should I change the color maybe? I'm gonna put in a different color just in case. So that's the decision boundary. Okay. Decision B. Right. So this W that we are talking about here correspond to the normal vector to the hyperplane, right? So the normal vector, it's a vector that points 90 degrees with respect to the hyperplane. So like it's in this position here. That's W, okay? You see that's like the normal vector, it could be like in any direction. So it could also be pointing in this direction if you want. So like that's just talking about like the direction, okay? Now, what's xi? Xi corresponds to this vector that leaves from the orange of the system to each one of these points. So those are xi's, right? Where I basically identifies which one is the point that I'm talking about, because this I equal to 1. This one, let's say, is I equal to 5, for example. You see? Any questions there? Okay, very good. Now, this is a dot product, I told you, right? So like this is a dot product. So if you remember, the dot product between two vectors, which is like, let me change the color again. You guys can understand that like both xi and w, they are vectors at this point, right? So like now I'm gonna perform the product of these two vectors. So like the product of xi and w, you can approximate that as being the magnitude of xi and the magnitude of w times the cosine between those two vectors, right? So if they are in the same direction, so let's talk about this case here, right? This guy is here. So if I get the xi for this point, right, and I do the dot product with w, I'm gonna get, let's say that like they were roughly, they were exactly in the same direction, right? So the cosine between them is 1, right? Because they're exactly in the same direction. Therefore, this is all a number greater than 0, right? So like, let's say that's a positive, therefore, right? So like, this is a positive number. So like greater than 0 is 1, right? So like we kept like, if it's greater than 1, greater than 0 is equal to 1, f of x. If it's like less than 0 is equal to -1, right? Which essentially would correspond to saying that I just want the sign of this function. Okay, so I perform the dot product between x, y, and w, right? And then I just get the sign of that. So like the output of this thing is going to be either 1 or -1. Okay, and then we said that, okay, so if that's the case, right? If I have a positive value, that means that like they are both agreeing in the direction that they are pointing to, right? Therefore, I have 0 for this loss. So like I don't need to do anything with respect to that. If they disagree, right, then I have a loss that's greater than 1, right? And therefore I need to do something with respect to that. I had to change something. I had to move this boundary around a little bit. Good? Any questions so far?
So
I'm gonna
graphically,
please.
the W vector would also start from the origin, right? And then by calculating the
Right.
dot product, we're just calculating the angle between them. when does this become negative? When they're like, when it looks the other direction of the plane? Is that when it turns negative, or?
Right, yeah, because if I'm talking about these points down here now, right? You see that's like the this vector, now it's pointing in this direction, right? So like the product between dw here and this point down here, right? It's gonna give me a negative number, right? But it's okay because like what goes in this formula here is the product of the prediction, which was -1, and the ground truth, which was also -1, right? Therefore, the product of -1 and -1 is 1 positive. That means that like I did the right prediction.
Yes.
Okay.
Yes.
Yes,
Okay.
and we're interested here not in the model of this vector, but only on its side, sign, or we should also take account of the value of this vector, or only on its sign, either positive or negative.
I did this sign to simplify things, but you see that the actual formula, you see here, doesn't take sign. So like it accounts also for like how far off were you, right? Which then like takes in consideration the angle between the two vectors. I'm simplifying that to say like, I'm just like either in this side of the decision boundary or this side of the decision boundary. If I do that, just take this sign, I'm gonna end up with a less optimal decision boundary, because you see that like any decision boundary that satisfies the separation, it's already good. If now I don't use sign, so I take like the actual product. Let me erase some of this stuff here. You guys cannot even see anymore the numbers. Yeah, so like if I take the actual value of this product, right? Now you see that I have like by how much were they different, right? That allows me to converge to the optimal decision boundary. Great point. Yeah, the sign here was just a matter of like simplifying the problem initially.
Yeah, I see.
Mm-hmm. Any other questions?
May I ask again a little bit more on, can you explain a little bit more on the hinge loss function? Is it,
Yeah.
yeah, sorry.
No, yeah, of course, yeah.
Stand
So
up.
like let me delete some of this stuff up here. Okay. So like how the hinge loss function works, right? So like, then. Okay, so like I have two components for the hinge loss, which is f of x. Let's do like this, and y. Okay, and here's gonna be the output, which is like 1 minus f of x times y. Okay, good, very well. So like what the hinge loss function does basically is to tell you like by how, like in which direction you're classifying the things and if they're correct or not, right? So like if you just want to know, am I classified correctly or not, you can take the sign of this, as we just said before, right? And why is that, right? So if, for example, f of x is 1 and y is equal to 1, right, in this case, then I have 1 minus 1 times 1, which is equal to 0, right? So that means that I have 0 misclassification. You see? Now, if the output of my model disagrees with the true label, let's say that like the output of my model was -1, and the ground truth data that I have is 1, therefore I have 1 minus 1 times 1, right? This is going to be equal to 2. Correct? So that means that I have a misclassification.
All right.
Okay? So that's the hinge.
Quantify of the misclassification, or the quantification of the misclassification. But what is the S16 on the
S,
like right above the y times it, like right under the SVM optimization title? what is the like the bracket? So the red
Oh,
word
that's a
is like
sign.
Sign.
S16, a sign.
Ah, it's sign. Sorry, it's sign. It's supposed to read like this.
Oh.
Sign.
no, sorry.
Yeah. Okay. Good.
Okay.
Good.
Yeah. Good.
What
Okay.
does sign mean?
Yeah. So sign means the following. So like I just want the sign of the output, right? So like let me
Oh,
here again.
like positive or negative, or
Positive or negative.
ah,
Perfect.
okay.
Yeah. Yeah. But then I translate that to a number, right? So like positive would be 1 and negative would be -1.
Mhm.
Okay.
And
Then
how?
we should
Go ahead.
minimize the sorry.
Go ahead.
Yeah, now we go to the process of optimizing that. So far, I only have explained to you the loss, right? Right, now I want you, we want to know how we should be changing the position, right, of this hyperplane. So remember that the position, let me do it one more time. The position essentially stands by like where this normal vector is. So that's W, right? So if I move the normal vector here, you see that the position of the hyperplane changed, right? And that's like how I change like where this decision boundary is, okay? It's by changing the weights of W, okay? So W is a vector, and this vector corresponds to like the coordinates of where this hyperplane is, okay? And we call it the weights, but like just for the sake of making it general, because we're going to be talking the weights of decision boundaries for neuronal networks as well. And they should just correspond to the coordinates that are defining the position of this hyperplane in this space. Okay, very well. So like I want to update the weights, right? The weights here with respect to each one of these terms that compose my loss, right? So like if I want to understand how these weights W, they are changing with respect to the weights that I chose in the previous iteration, right? I want to do the derivative of this function with respect to the weights. So I can understand how this function is changing every time that I do small increments or decrease on the values of W, okay? So we do that via computing the derivative of this function. So if you guys remember what the derivative is, right? So like, for example, in more general terms, let's say that I'm computing the derivative of x squared with respect to x, right? We have like, you probably, when you did calculus 1, you learned about like dropping this exponential down, right? So like, then you'd have 2x, right? So that's essentially what you're having here. So I'm computing the derivative of this function with respect to W. So this 2 drops down. So like then I have that the derivative of this first term is equal to 2 lambda W. Okay. Now I do exactly the same thing for the second term, right? So like the second term, I'm computing the derivative of this function, which like is exactly the same that you have here. Okay. I've computed this derivative with respect to the weights WK. Okay. So for the first term, which is just this one, okay, I had no W associated to it. So like if I compute the derivative of a constant, let's say a constant C, with respect to dx is equal to 0. So that's essentially what you get there, okay? And then if I compute this derivative with respect to the second term, right? So this is a product, right? So therefore, this one disappears, the W, and I get just the constant, which is like the minus yx. You see? So those are the only two terms that are going to be composing the actual loss, that the rules that I use to update the weights, right? So I get these two W, 2 lambda W, and I put it here. Okay. And then, oh, sorry. Okay. So this term is the one that's telling me like how well I did in my classification. It's here. Okay. And this term is the one that's penalizing the position of this hyperplane. Okay. So I'm transforming the weights. So like, remember again that the weights, they are defining the position of this hyperplane, right? Taking in consideration how many cases of mistakes I made, right? Which is now defined by this product, okay? Which again, this tells me by how much I change my classification every time that I make a small change in the weights that are defining the position of the hyperplane, okay? And this term tells me like what's the magnitude of this hyperplane, right? So like, what's the overall position that I have? So like, if I penalize also the magnitude of the hyperplane, that also pushes me towards not having just a good classification, which is this first term, but also being optimal. Okay. And then I have this term that's called the learning rate, which we're going to be talking a lot about once we get to neuronal networks. That tells me, okay, like take in consideration these terms that are telling me by how much you should be changing the weights and how that's going to impact your classification performance, right? Also the position of this hyperplane and change by this amount. So that's a scalar. That's basically multiplies like by how much you're going to be updating the weights. And this is like, what's the weight that you have? Like, what's the position of that normal vector, which is defining the position of the hyperplane, right? And it's gonna either add or subtract from it, depending on the value of this one, right? So like, if this is a negative value, this is gonna subtract from the weights or add, depending on what's the magnitude. And that's gonna be the next set of weights. So like, that's the updated position of this hyperplane for the next cycle. And then you keep moving these around, taking into consideration those two components of the loss. Okay, questions?
And what does this lambda refers to?
Yeah, that's a good question. So like this lambda, it's another scalar. So you're gonna see that in some case, even when you get the loss function for the SVM, you also have like some sort of another scalar for this component as well. Let's say a beta, you know, which are like by how much I wanna take in consideration, because right now, if I don't have a lambda or a beta here, let's say that was just like without this guy, you see that the weight that I assign, like how much importance I have for the misclassification component, which is this one, that's the misclassification, right? Is the same weight that I assign for the magnitude of this normal vector that's defining the position, right? So if you want to say like, you know what, actually I care more about having as many cases as possible as being correct. So like this is more important, right? For me, I assign a bigger weight to that one. So for example, this lambda, if I make a lambda, okay, that was supposed to be a lambda. If I make this lambda less than 1, right? Then I have higher weight in this guy, right? So like I give higher priority to like correct classifications than actually making the position of this hyperplane optimal.
Yeah, the intuition is understandable. Thank
you. Okay. Any other questions?
Why is it called the magnitude? Is it the angle of the hyperplane, this W, or it's like the normal vector, right? But ultimately it describes our separation plane, right?
Right. The thing about the magnitude, right, is that the rules are rational.
Oh, what is the two lines? What are we actually calculating? What's the metric that we're doing here? It's like the two lines and squared. What's the notation stand for?
You're talking about this one?
Yeah.
Yeah, so that's the norm.
The norm, okay. So it is magnitude, okay. But why?
Yeah.
But that's just the length of the normal vector. Why is that relevant?
Yeah, because that's a thing that I'm going to discuss like in greater details once we get to neuronal networks. But like, let me give you a little taste of it. So let's say that like, I told you that W stands for a vector, right? So like, imagine that it's a vector that sort of looks like this. Like I have numbers like 0.1, 0.35, 1000, you know? let's say that's like, okay, great. This gives me a decision boundary that already does the job. Okay. So like these already like perfect classification. Okay. Now, this is being multiplied by an X. Right? So the X also, let me be a little bit more consistent with the notation of a lot of vectors. So like this is being multiplied by an X. That's gonna have similar values, right? So like it's gonna be 0.25, blah, 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 right? You see that's like in this product, I have 0.1, 0.35, then I have 1000, right? This leads to a correct classification. Yeah, it does, right? But you see that like this corresponds to how much weight am I assigning to this specific element of the X space of features, right? So like, does it make sense? Sometimes not. And what happens is that like, as I have a little bit of noise, let's say that like during the process of training, the supported vector machine, I had value like 0.1 ranging all the way to 0.22, right? And that still led to like a good classification. But when I got new data, I actually got a 0.225. But because the magnitude of this weight was so big, it completely threw off like the classification of that point. So if I penalize the magnitude, I'm yeah, it's a regularization. Yeah, I have been fighting to not use this word out of context, but I'm glad that you know that. So yeah, it's a regularization technique.
But where does, so in our 2D example, like the most important kind of factor is the angle of the separation plane, essentially, right? So where?
Right. Yeah.
So where does that? I guess it's in the W, right? It's encoded in the based on.
Yeah, it's encoded in the
where it's
W.
pointing.
Yeah.
Yeah. Okay. Okay. Thank you.
Antonio, maybe a basic question, but this K in a subscript, so this is iteration, yeah? Or
yeah, it's iteration.
Updating updating the initial value of the vector, yeah?
Yeah, to some extent, but like this is like the most general formula, right? So for example, we have been talking about a hyperplane that's 1D, right? It's just a line. So like I only have one hyperplane to train. But like that's another thing that I was going to discuss later. Let's say that I need multiple hyperplanes to be able to classify something. So I have more categories, right? So like let's say that now I don't have just like the axis, but I have the circles and I got a couple of squares here. Okay, so now if I come with like one decision boundary, okay, yeah, I can separate the axis from the squares and the circles, but I don't separate the circles from the squares. So I need another W that corresponds to this one, right? So those are the W's that I have. So like that's like WK corresponds to each one of these normal vectors that talk about several hyperplane for separating the classes.
Okay, but still there is for each K, there is initial value, yeah?
Yeah.
And how you set this initial value? It's 001 or whatever.
Is usually given by like a Gaussian distribution. So like it's like sampled values that come from a Gaussian distribution. So like it looks like this, for example, right? Where here I would have like 1.0 and here I would have minus 1.0. Most of the values, like because they're being sampled from distribution, they would be like roughly here, right? So they are gonna be like near 0, like 0.5, you know, like some minus 0.35. And then in the process of like being trained, they're gonna be placed in the right place. But usually they are sampled from like a Gaussian distribution.
Okay, so it's a randomly sampled from the Gaussian. Yeah.
For the initialization, yes.
Yeah, and the Gaussian is probably defined according to the meaningful. So okay, here is a clear geometrical explanation of the of the problem. So yeah, that's why they yeah, okay.
Okay.
Mhm.
Now it's 1:35.
So may I ask again a little bit about the part, Antonio, you said about we'd have to decide whether we want to maximize the W or we want to maximize the hinge loss function. I can get the concept that maximize the hinge loss is kind of like to make more accurate, but what is the mean to make the maximize the W? Like in the
You're
2D
trying to minimize the W as well, the magnitude of W.
Okay, if like in the 2D example, what is the meaning of minimize the W? Is it
Yeah, so like minimize the W in this case, right? So let's think of that. I'm gonna delete this whole thing again. So here, let's go back to this example, right? Where I had these guys and these guys. So like now I'm gonna try to define a vector, right? That separates the two of them. So like, as we said before, I can have like multiple decision boundaries, like all of them satisfy the problem, right? But like, let's say that this model that is not being optimized for like minimizing the magnitude of W, decide to find this boundary here. Okay. So like, you see that for, I gonna give like 2 points, like passing through the orange, right? So like this is gonna be defined as the line that passed through 0, 0, and pass through the point x equal to 1000 and y equal to 0.001. Okay. So like, you see that this is perfectly fine line for a decision boundary. Okay. The problem is that if I compute the magnitude of this line, which like takes into consideration like these weights, you see that these weights here, they're all messed up, like 1000 compared to like 0.01, right? Now, if I minimize both of them, this is not going to be this discrepant, right? I'm going to have something that looks more like this, which is like what would happen if I'm also regularizing the magnitude of W, right? So like you see that this pushed me to have like a more optimal, so not just like correct classification, but also more optimal overall.
Okay.
These are all things that we're going to explore in more details once you get to neuronal networks. I'm just trying to like not overwhelm you with way too many details at this point.
Yeah, thank you very much.
We're going to discuss that with way more details once, because like you see that I'm discussing several things here that in theory I'm going to like break it down better in the future, right? Which is like the idea of gradients. So that's where we're going to talk about optimizers. I think I put that like in class 2 or 3, but like in order for us to understand at least the basics of like how this optimization works for SFM, we also need to understand a little bit about how we minimize the loss, right? So like we're going to discuss loss better in a little bit, right? Like next class probably, because today is over basically. We're going to discuss gradients, which implies like the use of optimizers, right? All of that's going to be described in more details later. But did you guys understand the overall idea here? Like the rationale between like the placement of the decision boundary, how we manage to use that to like leverage not just like having a good classification, but also the one that offers me like the maximum margin and therefore like more room for like potential mistakes, to correct potential mistakes. So I hope those are the key concepts that you managed to keep from this. Any other questions before we move on? I think we have 5 minutes still.
Yeah, and should we normalize our this axis before using this method? For example, if one of the axes will have like variance which are maybe hundreds, thousands times larger than other axes, it would dominate, or this method it will automatically like normalize our data, and we need to worry about this.
Always normalize your data. Like if you're before you get the data, always normalize it. That should be like step 0, you know. So like always normalize your data. So you shouldn't be having like your data set something that's ranging from like -1000 to 1000. Like what matters in the end is not the absolute value, but rather like what's the value with respect to the other data points. So like always normalize your data. Because
you also-
otherwise, yeah.
Yeah, my question was about, would you normalize for regression? Because in that case, you're interested in the final value, right?
What to normalize for regression?
Or would you normalize the values for regression if you're trying to predict something for temperatures, for instance?
No, yeah, we normalize the values for the regression too. Like you're talking about the labels, I assume, right?
Yeah, yeah. The target.
Yeah, we normalize. Yeah, we normalize the values as well for regression.
Okay. Thank you.
Okay, maybe I go on just one more slide, or should I leave this for the next lecture though? Yeah, so like so far, you see that we have been talking about how to use SVMs, the supported vectors, right, to perform a classification. So do you guys have any insights how we can turn this classification task in a regression task? And maybe I hear what you guys have to say and we stop here for the sake of time, and then we'll pick up from this place tomorrow, Friday. How do you guys have any like insights on how this might take place?
I mean, using just using the pictures that we're seeing right now, right? If instead we might want to find an optimal hyperplane that goes through the points where the margin of my supports that encompass all the points are as close to my hyperplane as possible. So maybe I'm trying to minimize that margin.
You got it. Yeah, that's exactly what we're going to be doing then for the next lecture. So we're going to see how we can make use of this same idea of the hyperplanes, right? But now we're trying to get all the points inside of this region defined by the support vectors, right? Instead of like having them outside of the support vectors. So we're going to see how we can adapt it in the next lecture. And then I'm going to stop here. Yeah. As I told you, like I always run out of time. So like we're gonna, but
we ask a lot of questions too, I think. So it's not just your work.
Yeah, I good. I'm very happy that we got a lot of questions. That means that you guys are really trying to understand the concepts, and I hope I managed to address at least part of it for now. If you didn't fully understand this rationale about like this normalization of the weights, why they are important, be in peace, because we're gonna investigate that in more details like in the coming lectures. Okay, like why you shouldn't have a weight like in this W vector that's like 6 times the magnitude of the other values, right? And we're going to understand exactly why that's the case once we get to like the importance of that for normalizations and optimization. Okay, any other questions then? So I'm going to stop here. And
yeah, I had another question.
Please, I have a question.
Go ahead.
Yeah.
Yeah, thank you. I know in optimization problem, we deal with constraints. Like I don't know if it works here. The hard constraint and soft constraint. I think that is where the weight comes in. If we have if we are adding weight to the hard constraint, that is those constraints that we really, really need for the optimization process, and we might leave the soft constraint out of it. I don't know if the same process works here.
Yeah, no, absolutely. And you see that like when you're going to start talking about support vector for regression, right? You see that the very second thing that I have here is the constraint, right? And why is the constraint important? Let's say that we are trying to do the classification. Let's go back to the classification just for 1 second, right? So let's say that this data set was actually noisier than what we are having here. Let me see if I have more space here. Yeah. So let's say that like instead of having such a clear separation between the classes, actually I have something that looks like this. So those are the axes, right? And then now I have these circles. Right? Now, linear classifier became way harder, right? because like saying that I want to satisfy this the placement of this the hyperplan in a place that gives me like the maximum separation no longer works, right? Because I have an actual mixture of the two distributions of data sets, right? So now I have to impose like, okay, so since you're not going to be able to just like give me one single hyperplan that gives me like this maximum separation, we have to come to the idea of like, okay, how much am I willing to allow the error to happen, right? Which basically stands for like how much deviation or how much mistakes you can still make, which essentially comes to like to the, yeah. So that's explicitly posed on the regression via this term, right? Which like how much deviation from the margin am I willing to have?
Yes, yes.
So like you have that also for like regression and for classification with support vector.
Okay, thank you.
Mm-hmm. Okay. Okay, guys. So let's stop here then. So what we're gonna have for the next lecture is gonna be the end of this one. So the support vector for regression, right? And then we're gonna discuss like several other things about like a little study case, it's like a toy data set. And then we're gonna finish with this tutorial using support vector machine for regression on the tree height data set. Okay. And okay, that was the first lecture. I hope that was not too much for a first lecture, but I'm very happy with the level of engagement here. Yeah, like thank you so much for all the questions. Keep it coming.
Okay, thank you very much, Antonio.